We're going to continue our discussion of clustering by talking about non-hierarchical clustering. And to do this, we're going to borrow from some slides made by Professor Andrew Moore, who's a professor of computer science at Carnegie Mellon University. So the way k-means clustering works is we start off with a fixed number of clusters. And if we look at this example where we have 2 dimensions plotted, you look at this and say there's probably 5 clusters here, maybe 4, but we're going to go with 5. And then we're going to say let's pick some starting points. Maybe they're picked at random, maybe they're the first few observations from the data, but here they are. You can see them here, 1, 2, 3, 4, 5. Those are the 5 starting points. And we're going to think of these points as centroids. And then the way the algorithm works is it says, let's take all of the points, say this one to start off with, for example. What's the distance between that and the first centroid, second centroid, third centroid, fourth centroid, and fifth centroid? And whichever one it's closest to, that point will be categorized as being in that group or cluster. And we're going to do that for all of the data points. And when we're finished, we're going to get something that looks like this. All of the data points in this region are closest to that centroid. All in this region are closest to that centroid, and so forth. And so now that we've got the clusters defined, we're going to calculate new centroids for each of the clusters. And you can see that this point here moves over to here. This point here gets pulled up here. This point here is pulled over here. And that gives us new centroids. And then you can guess what we're going to do next. We're going to reclassify all of the data once again by which centroid they're all closest to. So using the new centroids, we're now going to calculate the distance between each of the data points. So that one to there, there, there. And we do that for all of the points, and whichever one they're closest to, whichever centroid they're closest to, that's going to give us a new group. And so you can see here we have new groups, and as we step through these next slides, you'll see how these centroids are going to change, or rather the groups are going to change along with the centroids. And it keeps going on, and we can start to see now that this green group is up here. That's pretty well established. Blue, black, and purple, and then the red looks like it was over here, and it's going to start moving this direction, and you can see that eventually we're going to have these groups. So eventually the centroids are going to stop moving, and that's going to be our cue to stop the process. Now, in 2 dimensions, it's kind of easy to see what's going on, but what would happen in higher dimensions? I mean, here we looked at it and said looks like there's 5 groups, and sure enough, we were able to find 5 centroids that go along with those groups. But what if it wasn't clear, and or there were more dimensions that we are dealing with? Those are questions that we need to answer, and k-means is a tool for us to be able to answer those questions. And so picking the number k is often the hardest part of this. So let's look at this again. First of all, we're going to pick the number of clusters that we want. That's our k, and again, that's the hard part. Once we do that, we're going to start with k different clusters. So partition the data into k different clusters is going to be usually based on a random selection of k centroids, and at each step we're going to move each record to the cluster with the closest centroid, and then we're going to repeat that until the centroids stop moving. So how do we pick the value of k then? Well, there's a couple ways we can do it. We can go into it with a preconceived notion of how many segments we want there to be, market segments, for example. We could also experiment with the different k's and look at the outcomes. But what we really want to do, or most often want to do, is let the data speak. and we can look at the variation between and within the different clusters to be able to tell what the best number of clusters is for the data set. In JMP, we can specify a range of values that we want to try for k, and you would do that by saying number of clusters and optimal range of clusters. And then we can look at the output. Here we have when k is equal to 6. Remember, we were using the utilities data set, so there's 22 different observations. And so with six clusters, this tells us how many individuals there are in each cluster. So the first one has 1, second one has 6, 6, 5, 1, and 3. And then we can go and look at the cluster means for each of the clusters and each of the variables. So cluster number 1 has a mean of 0.67 for fixed, 6.4 for ROR, 136 for cost, and so forth. And we know there's only one observation there, so that means the standard deviation for each of those is going to be 0. That's a constant, basically. Same thing with group cluster number 5. We got zeros here. Once we have summary statistics for all of the different clusters and variables, we can do things like parallel coordinate plots for each of the clusters, and this can be informative. We can also look at scatter plots, and these will help us understand the separation and the overlap of all the different clusters. We can also look at a scatter plot matrix. You get the same thing for all of the variables individually, or sorry, pairwise. So in summary, cluster analysis is what we would call an exploratory tool, one that you would use to look at the data and try and come up with a firm understanding of what kind of patterns and relationships there are in the data. It turns out it's only useful if there are meaningful clusters, if you can give names to the clusters that you come up with. You can use hierarchical clustering to see a visual representation by way of a dendrogram as to how the different observations cluster with each other. And non-hierarchical clustering is pretty easy to do. It's not too taxing on the computer and seems to be more stable when you have at least larger data sets, but requires the user to set a value of k, or go in and try different values of k and decide which one works best. You can use both methods. In fact, one way to help decide what the best value of k would be is to use hierarchical clustering, look at the dendrogram, and use that as a basis for picking a value of k. But you always want to be a little bit wary about this, because sometimes pure randomness can define clusters that will look like clusters but are really due to randomness. So you want to be a little bit careful about that. And that's the end of what we have for cluster analysis. There will be at least one other video in this week folder that shows some of the examples, or does one of the homework questions from the text, and will help with looking at the between and within measures of variation. Okay, give me a shout out with an email if you have any questions about this, and we'll see you in the next video.